So today we're going to look at lesson 6-3, which is on rational functions and graphing them. So we're going to look at everything that you should possibly need to know when it comes to graphing a rational function. So you either have a continuous graph, which typically with rational functions you don't normally have a continuous graph. That's a graph with no jumps, breaks, or holes. So you could leave your pencil down and never lift it up, and then it has a graph. Or if you have a discontinuous graph, it means you have a jump, break, or a hole. So as you're going along a line, you have to jump and then go someplace else, move it, jump, go someplace else. And so we're going to look mostly at discontinuous graphs today. So you have points of discontinuity, and they will either be removable or non-removable. So for instance here, we have a point of discontinuity here at x minus 3, because remember that denominator cannot equal 0. So if I take my x minus 3 and set it equal to 0, if x were 3, I would have a value of 0 in the denominator, which is not possible. So that's how we get that point of discontinuity here. But the question is it removable or non-removable? So if a point of discontinuity is removable, it can be removed by factoring. So that's important. I would highlight that. And then it becomes a hole. So if it's removable by factoring, it becomes a hole. So if you look at this example here, I can factor the numerator as x plus 4 and x minus 4. And then your denominator is x plus 4. So prior to today, we would have set this denominator of x plus 4 equal to 0, and we would have had an asymptote at x equals negative 4, because that would cause a 0 in the denominator. But because I can remove that discontinuity by factoring, I end up with x minus 4 as my graph. So the graph of this actually looks like the graph of a linear equation here, but there's a hole in this graph. So if you were to put this in your calculator, and go ahead and put it in your calculator, you'd have to put this in parentheses and this in parentheses. And so if you graph that, it would look like this. It would look like a graph of a straight line. So it looks like it's a continuous graph, but there's actually a hole along this line. And the hole occurs here where this discontinuity was removed. So if you go to your table of values and you try to put in negative 4 in for x, your calculator is going to tell you that it is not possible. Now, of course, if you put this in your calculator, you're going to be able to put in negative 4 and you'll get a negative 8. Because your calculator doesn't understand that this came from this original problem. So if I put negative 4 into the calculator, it's going to show an error. But I have to figure out where that hole is. So to figure out where the hole is, you want to take what was removed, a value of x equals negative 4 here, and you're going to put it in your resulting equation here. So our hole is going to be at an x value of negative 4, and then if I put negative 4 in here, negative 4 minus 4 is negative 8. I get a y value of negative 8. So at negative 4, negative 8, see if I can figure out where that might be. So then this graph would continue all the way down here. Whoops, all the way down here. It's a little thick, sorry. So I would have a hole on my graph right there. So my discontinuity occurs as I follow along this graph. I'd have to jump that hole and land on the other side and keep going. So this is a discontinuous graph because it has a hole. Actually, it has a hole, not even a jump. A non-removable discontinuity means that it is not removable by factoring. So that's what we were working with yesterday in 6-2. So if you look at this problem, you can still factor it. So the top stays x plus 3, and the denominator factors as x plus 2, x minus 2. None of these cancel. And so you do have a discontinuity here and a discontinuity here. They are not removable because they did not go away via factoring. So you actually have vertical asymptotes at both of these points. So if I set x plus 2 equal to 0, I would get x equals negative 2. And if I set x minus 2 equal to 0, I would get x equals 2. So these are going to be vertical asymptotes. I'm just going to abbreviate that. So if I were to graph this, you would have a vertical asymptote here and here. So you're going to have some sort of a graph, and we're not going to take the time to graph it all right here, but you could have some graph over here, some in here, and some over here. All right, so let's go ahead and look at example 1. So for example 1, we're going to graph this whole function, and we're going to determine if there are any discontinuities. So all we care about are holes, asymptotes. We're going to start looking at horizontal asymptotes. But for right now, I'm going to start with my vertical asymptote. So I'm going to take this denominator right here, x squared, and I'm going to set it equal to 0. To solve for x, I'm going to take the square root of both sides, and I have to do plus or minus the square root on the other side. So I get x equals plus or minus 0, which just means x equals 0. So that's one of my asymptotes, so I'm going to immediately put that in here, x equals 0. So that's a discontinuity. And then for right now, you're not going to know how to find your horizontal asymptotes until you graph it. I'm going to show you later how to find those horizontal asymptotes. But for right now, we're going to graph it. So I'm going to graph a few. I'm going to graph a few values to the left and a few values to the right. We can ignore this x equals 0 because we know that x can't possibly be 0. So I'm going to choose negative 3, negative 2, negative 1, 1, 2, and 3. So 1 over negative 3 squared would be 1 over 9. 1 over negative 2 squared is 1 over 4. 1 over negative 1 squared is going to be 1. 1 over 1 squared is 1. 1 over 2 squared is 1/4. And 1 over 3 squared is 1/9. So let's graph those values, or at least the ones I can. So I can graph the negative 3 and 1/9, which is just right there, really close to the x-axis. Negative 2 and 1/4, a little further from the x-axis. Negative 1, 1, 1, 1, and then 2 and 1/4, and then 3 1/9. So this graph appears to be hugging the x-axis, but not crossing it. And if you think about it, if this graph crossed the x-axis, then all of a sudden the y values would end up negative. There is no way for the y value to be negative no matter what value I put in for x, because I'm going to square it. So this has no possibility of becoming negative, as you see here. So that means that this right here must be a horizontal asymptote, y equals 0. So your horizontal asymptote is y equals 0. So there's your discontinuities right there. So for this particular graph, they have already factored the numerator and the denominator for you. So to look for discontinuities, the first thing I notice is that these are going to cancel. So this is normally a discontinuity. It would normally be a vertical asymptote, but as soon as it cancels with something in the numerator, it becomes a removable discontinuity, and removable discontinuities are holes. So I'm going to note that as a removable discontinuity, which is a hole. So we've got to find the ordered pair for that hole. All right, so I know that I'm going to take the x minus 2, which was removed, and set it equal to 0. That means the x value of my hole is 2. Then I'm going to take this value for x to find the y value of the hole and plug it into the resulting equation. So I'm going to take y equals x plus 1, and I'm going to put the 2 in here. So I get y equals 2 plus 1. And so my y value is going to equal 3. So my hole is at 2, 3. All right, so I'm going to go ahead and graph this. And remember, I'm graphing the resulting equation. So this is a linear function in the form of mx plus b. So my y-intercept is going to be 1. So I'm going to plot a point at 1. And then my slope is going to be 1 over 1, or negative 1 over negative 1. But I want to plot my hole at 2, 3. So as I stair-step my slope, so then I can draw my line through it. So as you can see that this is a discontinuous graph because of the hole right here. So then you go ahead and try number 3 on your own. And by the way, number 2 did not have any horizontal asymptotes, so wasn't approaching anything for the y value. But go ahead and try this one. Look to see if there is, and there will be, a horizontal asymptote. So stop the video, try it on your own, and then restart it. Okay, so I'm going to look for, there are no removable discontinuities because this is fully factored and this is fully factored, and you cannot cancel the x's because of the plus minus outside of parentheses. So there are discontinuities, but they are not removable. So these would be non-removable. discontinuities. And that would be a vertical asymptote. I couldn't think of it there for a second, sorry. So you get x minus 2 equals 0. Solve for x. You're going to add 2. So you get x equals 2 as a vertical asymptote. So I'm going to start with plotting that first. All right, so then I don't know anything about this, so I'm going to do a table of values because I haven't told you how to find the horizontal asymptotes yet. So I'm going to choose some values to the left and some values to the right. So let's choose, let's go -4, -3, -2, -1. I can choose 0 this time. 1, and I'm going to choose not 2, but 3, 4, and 5. I'm just going to choose several values just so you can see an idea of what's going on. They're pretty easy to plug into. So all I'm doing is taking this x value and plugging it in here and here. And so I'm just going to talk through that. So a -4 plus 1 is a -3 divided by a -4 minus 2 is -6, which equals 1/2. So when x is -4, y is -1/2. Oh, positive 1/2. Sorry. So I'm right about there. All right, so -3 plus 1 is -2. -3 minus 2 is -5. So that gives me a positive 2/5. So -3, 2/5, a little bit closer to the x-axis. And then -1 plus 1 is 0. Oh, I didn't do the -2. -2 plus 1 is -1. -2 minus 2 is -4. So that gives me positive 1/4. So -2, 1/4. So even closer to the x-axis. And then -1 plus 1 is 0. Divided by -1 minus 2 is -3, which equals 0. So -1, 0. That actually is our x-intercept. And then 0 plus 1 is 1. 0 minus 2 is -2. So I get 0 and -1/2, and that ends up being our y-intercept. 1 plus 1 is 2. 1 minus 2 is -1, so that equals -2. And then 3 plus 1 is 4. And then 3 minus 2 is 1. So that equals 4. And then 4 plus 1 is 5 over 4 minus 2 is 2. So that equals 2 and 1/2. So 4, 2 1/2, so right about here. And then 5 plus 1 is 6. 5 minus 2 is 3, and so that is 2. Now the question is, how far is this going to go down, to what number? So I'm going to choose a really big number, 10, maybe 100, or maybe 1,000,000. So if I put 10 up here, 10 plus 1 is 11. 10 minus 2 is 8. 11 over 8 is 1 and 3/8. Okay, so what if I put 100 in there? 100 plus 1 is 101. 100 minus 2 is 98. So 101 over 98 is going to be 1 and 3 98ths. That's really close to 1. And if I put a million in there, it's still going to be 1,000,001 over 999,998. So that's going to be like 1 and something out of 999,998. It's going to be really close to 1. So what you're seeing is a horizontal asymptote of y equals 1. And so this graph is looking like this. But I will teach you and show you how we can find this without just graphing and trying to guess, because these asymptotes actually give us the shape of our graph. All right, so for example 2, you were to find any points of discontinuity, whether they're removable or not removable, and determine which ones they are, state your domain, and find the x and y-intercepts. So for all 3 of these. So let's just go back and look at what the domain is for these 2 before you do the domain on these 3 below. So for here, remember you're walking the x-axis, in any time that you reach a hole or a discontinuity is going to create you to jump and go on. So for here, although I don't have anything right along the x-axis, I do have this hole right down here at 2. So as I go from negative infinity, once I reach the x value of 2, that creates me having to jump over that hole. So my domain is going to go from negative infinity. I'm going to reach the x value of 2, and then I have to leap over that hole on this line, and then I can continue forever. But the only x value that I can't have is 2. So it creates this break, if you will, in between negative infinity and infinity. So same thing is going to happen here for my domain. I'm going to be going all along here, and I hit this wall. So asymptotes also count as affecting your domain. So I'm going to go out along here from negative infinity. I hit this wall, and I have to jump it at 2 and continue on. So that domain looks identical to the domain we just looked at. Negative infinity till I hit 2. I have to leap over the wall and then go on the other side of 2, and then I can go to positive infinity. So I want you to go ahead, and you don't have to graph these, just find the points of discontinuity. Actually, I'll do A with you first so I can show you the x and y intercepts, and then I'll have you do the other ones on your own. So let's straighten this out, make it bigger. Okay, so first I want to look at the fully factored form. So the numerator cannot factor, but the denominator is x plus 2, x minus 2. So there are no values, no factors that I can cancel out. So I don't have any removable discontinuities. But because I have factors in the denominator, I do have some discontinuities, but they are non-removable, which means that they're going to be vertical asymptotes. So my vertical asymptote is going to come from setting the x plus 2 equal to 0 and setting the x minus 2 equal to 0. So on the left, if I subtract 2, I get x equals negative 2, and on the right, if I add 2, I get x equals positive 2. So both of these are non-removable. Discontinuities. They are vertical asymptotes. All right, so then the other thing that we have to find is we have to state the domain. And so any kind of discontinuity will affect your domain. So remember, as I go along the x-axis, I'm going to reach an asymptote, a wall, here at -2, then I'm going to go and have to reach another wall. So I'm going to have to jump a wall twice. So my domain will be, I'm going to start at -infinity, and I come to the wall, that vertical asymptote, at -2. I have to jump the wall, so it creates a break in my domain, and I end up on the other side of that wall. Then I continue walking until I reach the second wall at 2, and I have to jump over that wall, creating another break, and then now I'm on the other side of that 2, and I can go to +infinity. Now, they want to know what is your x and y intercept. So to find x and y intercepts, let me get a better color. All right, so for your x-intercept, that's the harder one to find. 100% of the time, the other value, in this case y, will be 0. So I'm going to set in the original problem y equal to 0. So you have to think about this logically. The only way for this fraction to have a value of 0 is if the numerator is 0. I don't care about the denominator. If I have 0 over anything, the value of that fraction is going to be 0. So theoretically, I can just ignore that denominator. I only care about the numerator. Since there is no variable here in the numerator, there is no possible way that this numerator in this fraction could be 0. So this does not have an x-intercept. There is none, and that's possible. So this graph does not cross the x-axis. So let's look at the y-intercept. The y-intercept is much easier to find. So for the y-intercept, you let the other value x be 0. So I have y equals 1 over, and I'm substituting in for x this time. So I'm going to put in 0 for x. And so I get y equals 1 over -4. So I get -1/4. So that means that my y-intercept has an x value of 0 and a y value of -1/4. So now you go ahead and find B and C. So go ahead and pause the video, see how you do, find the points of discontinuity, determine if they're removable or non-removable, find the domain, and the x and y-intercepts. Okay, so I'm going to start by factoring. So the numerator factors as x plus 1 and x minus 1. The denominator, however, does not factor. Since the denominator does not factor, it does not cancel with this one or this one, so there are no removable discontinuities. And in fact, if I try to set the denominator equal to 0, let's just try to find any discontinuities. So I'm going to take the x squared plus 1 and set it equal to 0. There is no way that I can make x squared into a -1 so that it combines it with 1 to make a 0. Because, for instance, if I try to solve for x, I would subtract 1, and then I would take the square root of both sides, and I'd have to do plus or minus the square root of -1, which is not possible. You cannot take the square root of a negative number. You would end up with an I, which means we're not going to cross the x-axis. There is no discontinuity as far as a vertical asymptote. There's no hole because I was not able to remove any factors. So since your vertical asymptotes come from the denominator and it's not possible to make this denominator into 0, there are none. So that means your domain, because discontinuities are the only thing that affects your domain, is going to be all real numbers. So it goes from -infinity to +infinity, no breaks. Then we want to find our x-intercepts and our y-intercept. So let's start there. Let's get a better color. All right, so for our x-intercept, we are going to let y equal 0. And so I have 0 for my y equals x squared minus 1 over x squared plus 1. So remember, the only way for this fraction here to be 0 is if the numerator is 0. So I really only care about the numerator here. So I'm going to ignore the denominator, and I am just going to look at 0 equals x squared minus 1 for my x-intercept. So I can factor that. X plus 1, x minus 1. And if you set each of these equal to 0, your x is going to equal -1, and x is going to equal +1. That means that you have two x-intercepts, one here and one here. So we have to find the y value, which you already know is 0. So I'm going to go ahead and write those out. So I have -1, 0 as one, and 1, 0 as the other. So there's your two x-intercepts. Then your y-intercept, you are going to let x equal 0. Remember, this is the easier one. So you get y equals you're going to substitute in 0 for your x, and you get -1 over 1, so y is equal to -1. So you only have one y-intercept, and so that is going to be 0, -1. All right, let's look at C. So for C, it is factorable, and it factors into the numerator is not factorable, so that stays the same. But the denominator, the factors of 2 that add to give you 3, are 1 and 2. Now in this one, you have a removable discontinuity. And so that occurs at x plus 1, because that's what we removed. So I'm going to set it equal to 0. So the x value is -1, and this is going to be a whole. So since it's a whole, I have to find the y value, and we get that from the resulting equation. So this is the equation that we end up graphing. So I'm going to plug -1 in for this x. So to get my y value, I'm going to plug the -1 in here, and I get 1 over 1, so my y is equal to 1. So my whole is going to have a value of -1, +1. That affects our domain, and so does our non-removable discontinuity. So your non-removable comes from the x plus 2. So this one was removable, so we used it to find the whole. This one is not removable, so we have to use it to find its asymptote. So this is going to be a vertical asymptote. So if I solve for x by subtracting 2, I get x equals -2. So that's your vertical asymptote. Both of these affect your domain. So because -2 is smaller than -1, I'm going to hit first. So I'm going to go from -infinity. I'm going to reach the asymptote at -2, and I have to jump that wall, which creates a break. Then I go from the wall at -2 to the hole at -1. So I'm going to have to jump the hole, which causes another break. And then I can go from the hole at -1 all the way to +infinity. The only thing that's left is our x and y-intercepts. So let's look at those. So my x-intercept, I am going to let y equal 0. All right, so I would prefer, and you can find your x and y-intercepts in either the original or the new equation. It would just be simpler to plug into the new one. So that's what I'm going to do. So I'm going to put in 0 for y, and then I've got equals 1 over instead of x. Oh, of course I wanted my x there, because I'm solving for x. Okay, so the only way to make this fraction equal to 0 is to look at that numerator. So right there. So your numerator has no ability to become 0, so there's no way that I can have an x-intercept. So there is none for the x-intercept. For the y-intercept, I'm going to let x equal 0. So I'm going to do y equals 1 over, but this time I'm plugging in 0 for the x. So I end up with 1/2, so y equals 1/2. So my ordered pair is going to be 0, 1/2. All right, then for 3, you're just going to find the vertical asymptotes for the graph, nothing else. Now, some of these are going to end up being holes, remember, versus a vertical asymptote. So if it's removable by factoring, it's a hole. And if it's not removable by factoring, it becomes a vertical asymptote. So you should know by now how to do these. So go ahead and pause the video, factor if it's not factored. If a factor gets removed, it's a hole, so it's not what we're looking for. Whatever's left over is a vertical asymptote. So pause the video and do this one on your own. Okay, so for part A, it's already factored for you, and none of the factors cancel. So there are no removable discontinuities, so there are no holes. So that means that these are left in the denominator, and they will create your vertical asymptotes. So I get 1 by using x minus 1 is equal to 0, and if I solve, I get x equals 1. So there's one of them. And the other I get from setting x plus 3 equal to 0 and solving, I get x equals -3. So when you look at B, now, however, this is factored for you, and those factors cancel. So this right here is a removable discontinuity, meaning it's a hole. Well, that's not what they're looking for. So instead, I'm going to use this one for my vertical asymptote because it's left over. So x plus 3 equals 0. X equals -3 would be my vertical asymptote. And then finally C, you have to factor C on your own. X squared minus 1 factors as x plus 1 and x minus 1 all over x plus 1. So this one has a removable discontinuity. So this is going to be a hole. There is nothing left in the denominator. So there are no vertical asymptotes. Then let's talk about how do we find horizontal asymptotes. So horizontal asymptotes, I'm going to leave a little bit of room so I can give you an example. Horizontal asymptotes are determined based upon looking at the degree of the numerator and comparing it to the degree of the denominator. So I always like to view the first one. We've done a lot where there's been a horizontal asymptote of y equals 0, because there's only 3 possibilities. Y equals 0, no horizontal asymptote, or this ratio of a to b. This ratio of a to b is the ratio of the leading coefficients of top to bottom, numerator to denominator. Okay, so for example, if I have a degree of a numerator that's less than the degree of a denominator. My perfect example is our parent function, 1 over x. Make that a lovely x. So the degree of the numerator here, because it's a constant, is 0. The degree of the denominator here, x to the first, is 1. So if I go and I compare my numerator to my denominator, I'm going to get 0 for my numerator, 1 for my denominator. Since 0 is less than 1, you will have the asymptote of y equals 0. And we definitely saw that because the graph of this looks like this. And we had a branch here and a branch here. But we saw that it had this y equals 0 asymptote. There's no way that y could ever have a value of 0 because the numerator can't be 0. So anytime you have this situation, so I could also have, let me give you another one. So I could have an example here of x squared minus 1 over x cubed plus 2. This is also going to have, you got x squared, which is a degree of 2, x cubed, which is a degree of 3. The numerator is smaller than the denominator. You're going to have y equals 0 as your horizontal asymptote. Now, how do you get no horizontal asymptote? The degree of the numerator is greater than the degree of the denominator. So, for instance, you might have x cubed plus 2 over x squared minus 1. So this particular one happens to be a very funky graph, but if you go ahead and put this in your calculator with this in parentheses and this in parentheses, you'll see a really funky graph, but there is no horizontal line that you could draw through this graph where there would not be a graph, so there is no horizontal asymptote. Then, what if the degree of the numerator is exactly equal to the degree of the denominator? That might be something that looks like this. 3x squared plus 5 over 4x squared plus 2. So now you have the degree of the numerator is 2, the degree of the denominator is 2, they are exactly equal. So all you do is look at the leading terms and look at their coefficients. This is A and this is B. So that means in this case, my horizontal asymptote is going to be y equals the 3 over the 4, because I'm just looking at those right there. So this becomes my horizontal asymptote. If you don't believe me, graph it and look for yourself. Okay, so we only have a couple left. So what I want you to do is just name the horizontal asymptotes for A, B, and C based upon what we just did. So I'm going to start off by looking at the degree of the numerator and compare that to the degree of the denominator. And so pause the video, find the numerator and denominator, look at your table above and see if you can figure it out, then restart the video. All right, so in this particular example, the degree of the numerator is 1 and the denominator is 1. So I have 1 to 1, that's equal. Since they're equal, then we want to look at the coefficients of the leading terms, which are negative 8 and 2. So y is going to equal negative 8 over 2. So y is going to equal negative 4. That becomes your horizontal asymptote. In example B, the degree of the numerator versus the degree of the denominator. So the numerator has a degree of 1. The denominator has a degree of 2. Well, 1 is less than 2, which means that you should have y equals 0 as your horizontal asymptote. Then the last one is C. If I compare the degree of my numerator to the degree of my denominator, my numerator has a degree of 2. My denominator has a degree of 1. The numerator is greater than the denominator, so there is no horizontal asymptote. right, then we just have these last two to graph and we are done. So all I want you to do is take everything that we've learned. I want you to find the vertical and horizontal asymptotes, find any holes, then use those to help you shape the graph. And then finally you might have to use a table of values to choose some graphs. So you can either stop the video and do it on your own, or I can walk you through it. It's your choice. All right, so the first thing I'm going to always do is factor. So x plus 3, and then this factors as x plus 3, x minus 2. So the first thing I notice is that the x plus 3's are gone. So what that means, it's a removable discontinuity, which is a hole. And I know the x value of my hole is going to be -3. Why -3? Because if I set this equal to 0, my x value will be -3. Then I need to look at the resulting function, which is 1 over x minus 2. To find my hole, I need to put the -3 in here. Well, -3 minus 2 is -5. So my y value is going to be 1 over -5. So I know I have a hole at -3, -1/5. It's really hard to put a hole there, but it's really not touching the x-axis, but it is. So there's that one. Then I have a vertical asymptote caused by this one right here that's left behind. So it's a non-removable discontinuity. If I set that equal to 0, I'm going to get x is equal to 2. So I'm going to graph that as a vertical asymptote. Then I want to see if there's any horizontal asymptotes. So I want to compare the degree of my numerator to the degree of my denominator. And I always want to look at the original. So my original is 1 to 2. 1 to 2. So 1 is less than 2. So I should have a horizontal asymptote of y equals 0. Then I would want to find my x and y intercepts. So my x-intercept, I'm going to let y equal 0. So if I let y equal 0, so 0 equals all of this. Remember, for y to be 0, the numerator has to have a way to be 0. Since the numerator here cannot be 0, and if you think about it, one of our asymptotes is the x-axis, so the graph can't cross the x-axis, there is going to be none. For my y-intercept, that's much easier to find because we're going to let x be 0. So if I plug 0 in here for x, and remember you can plug it into the resulting one, so if I plug in 0 here, I get 1 over -2. So I get 0, -1/2. So there's my y-intercept. So I know for a fact I'm going to have a branch here, probably go on like this. I need to choose some other values over here because I imagine my other branch is over here, but I'm not 100% positive. So I'm going to choose maybe 3 and 4 to plug in to the resulting equation. So xy value, I'm going to choose 3 and 4. I might choose more if I need to. So if I put 3 in here, I get 3 minus 2 is 1. 1 over 1 is 1. So I'm going to plot the point 3, 1. And then let's plug in 4. 4 minus 2 is 2. So I get 1/2. So as x is 4, we get 1/2. So my guess is that we are going to have a branch that goes like this. And that's it. For the, oops. Clearly I didn't take that off. So for the last one, we're going to go through the same process. So I'm going to start off by factoring. And I don't like the fact that my x comes second. So I'm going to actually factor out a -1 here, which means it's going to change this factor, instead of 2 minus x, it'll change it into x minus 2, because if I factor out a negative 1 from the x, I get a positive 1 for my x, and if I factor a negative 1 out for my 2, I get a negative for my 2. And the reason for that is so that I could maybe cancel it with my denominator. My denominator factors as x plus 2 and x minus 2. So this becomes a removable discontinuity, which is a hole. So my hole is going to have an x value of 2, mostly because if I set this equal to 0, x would be 2. So then my resulting equation is negative 1 over x plus 2. So then I want to find my y value of this hole, I want to take the 2 and put it in here. 2 plus 2 is 4, so I'm going to get negative 1 over 4. So I'm immediately drawing a hole at 2, negative 1/4. So really close to the x-axis there. Then I want to look at what's left over, because what's left over here is a non-removable discontinuity, which is my vertical asymptote. So I have a vertical asymptote at x equals negative 2. I set this equal to 0, and I get x equals negative 2. So I'm going to plot that. Then I want to find my horizontal asymptote. So to find that, I'm going to compare my numerator to my denominator, the degrees. The degree of my original numerator here, this is my highest degree term versus this one. My degree here is 1. And my degree in the denominator is 2. Because 1 is less than 2, I automatically will have y equals 0 as my horizontal asymptote. Then I need an x and y-intercept. So for my x-intercept, again, because this is my horizontal asymptote, I am not going to have an x-intercept. There's no even reason to try, so I know that there's none. For my y-intercept, that's the easier one to find. I'm going to let x equal 0. So I have y equals, and then negative 1 over my x is 0. So I end up with y equaling negative 1/2. So my x-intercept is going to, or my y-intercept is going to be 0, negative 1/2. Then I just need to choose some x and y values to plug in to kind of give me some more shape to my graph. So I'd like to find out how close I am here, so I'm actually going to try to plug in negative 1 and see what that gives me. So if I put negative 1 into here, negative 1 plus 2 is positive 1. Negative 1 over positive 1 is negative 1. So at negative 1, negative, let me see if I can, all right, so it's going to look like these two are really close, but there we go. So I know that based upon my hole and these 2 points, I'm going to have a branch that looks like this. Then I have to figure out, does my other branch go here, which is where I'm guessing it does, or over here? But I'm guessing it's going to be over here. So I'm going to choose negative 3, negative 4, negative 5. So if I plug negative 3 in here, negative 3 plus 2 is negative 1. Negative 1 over negative 1 is positive 1. So I am over here where I thought I would be. And then plug in negative 4. Negative 4 plus 2 is negative 2. The two negatives are going to cancel, and I'm going to have 1/2. And I imagine negative 5 is going to get me really closer, which it is. So I'm not even going to plug in negative 5. I know based upon this, that my branch is going to look like that. And that's it. It really doesn't take very long once you get all the process down. All you need to do is find removable discontinuities, non-removable discontinuities, your horizontal asymptote, X and Y intercepts, and then any additional points you might need to fill in the shape of your graph. That's it. Easy. All right, text me with questions.